Start to talk about statistical inference by discussing confidence intervals. So in the concepts, we need to describe the reasoning for statistical estimation, talk about the margin of error and the confidence level, describe confidence intervals for a population mean, and then we'll talk about how the confidence intervals behave. Now, after we have selected a sample, we know everything we need to know about the particular sample. But the reason for taking a sample is to infer from that data some conclusion about the wider population that's being represented by the sample. Statistical inference provides methods for drawing conclusions about a population from sample data. So we have this cycle again. We have a population in mind. We take a sample of individuals from the population, and then we infer something about the population based on the sample. So this chapter presents the basic reasoning of statistical inference. We'll start with something that's a little bit too simple to be realistic, but hopefully it'll get the point across. So, some of the conditions for inference about a mean. We have a simple random sample from the population. There is no non-response or other difficulty which would suggest our sample is not representative. And let's assume that the variable we measure has an exactly normal distribution. That's unrealistic, but we'll assume that for now. And we don't know the population mean. That's what we want to know about. But suppose that we do know the population standard deviation. Again, unrealistic, but for purpose of illustration, we'll use that. So the conditions that we have, all of these things, are all very unrealistic. We'll correct that later. Okay, so BMI, body mass index, is used to screen for potential weight problems. A BMI less than 18.5 is considered underweight, and a BMI over 25 is considered overweight. So suppose we have a sample of 654 women aged 20 to 29 with a mean BMI score of 26.8. What can we say about the entire population of 18 million women aged 20 to 29 based on this sample? Actually, quite a lot. For now, let's assume the distribution of BMI scores is approximately normal and has a standard deviation of 7.5. The central limit theorem says that the distribution of sample means of size 654 is approximately normal with a standard deviation of 7.5 divided by the square root of 654, or about 0.3. And the mean of this distribution of sample means is exactly equal to the population mean. And that's something we want to know. So, since the sample mean is 26.8, we could guess that the population mean is somewhere around 26.8. How close to that value, 26.8, is the population mean likely to be? To answer this question, we need to ask another question. How would the sample mean, x bar, vary if we took many random samples of size 654 from the population? Well, since the population is normal, the distribution of sample means is also normal. The mean of the sampling distribution of means is the same as the mean of the population distribution. The standard deviation of the distribution of sample means for simple random samples of size 654 is sigma divided by square root of n, or 7.5 divided by the square root of 654, which is about 0.3. So again, we take from the population, we take simple random samples of size 654, we get different means, and we look at the sampling distribution of those means. So we don't know what the population mean is, but we can use the sample mean to obtain an estimate for the population mean. So if you remember, the 95% part of the 68, 95, 99.7 rule says for this normal distribution, 95% of sample means will fall within 2 standard deviations of the mean. So we don't know what the mean is, but we do know that 95% of the sample means will fall within 2 standard deviations of that unknown mean. So for all samples of size 654, 95% of sample means are between 0.6 BMI units of the population mean. So we are 95% sure that our sample mean, 26.8, is within minus 0.6 and plus 0.6 BMI units of the actual population mean. That's somewhere along here. Now let's construct an interval that is 0.6 units below and above a sample mean. So remember that 0.6 represents 2 standard deviations. So we'll start with the sample mean, x bar. We add 2 standard deviations, and we subtract 2 standard deviations. We get an interval around the sample mean like so. So for the BMI example we have, we can calculate 26.8 minus 0.6 and 26.8 plus 0.6. So the interval is from 26.2 to 27.4. Now, 95% of sample means fall within 2 standard deviations of the mean. So for any particular sample, we have these sample means kind of all over the place. 95% of the time, the mean will fall in the pink area. 5% of the time, it'll fall outside of that area. So this also means that if we consider this interval that we've constructed, it means that 95% of those intervals contain the population mean. That is to say, in the first case, that interval around a sample mean contains the population mean. This one also contains the population mean. This one contains the population mean. Oops, that one doesn't. So this interval missed, but that only happens in 5% of the samples. So here's the big idea. The sampling distribution of x bar tells us how close to the population value the sample mean x bar is likely to be. All confidence intervals we construct will have a form similar to this one, an estimate plus and minus some margin of error. We call it a confidence interval. This is constructing a confidence interval. A level C confidence interval for a parameter has 2 parts. An interval calculated from the data, which has the form estimate plus or minus margin of error, and a confidence level C, which gives the probability that the interval will capture the true parameter value in repeated samples. That is, the confidence level is the success rate for the method. We usually choose a confidence level of 90% or higher because we want to be quite sure of our conclusions. The most common confidence level is 95%. So, the confidence level is the overall capture rate if the method is used many times. The sample mean will vary from sample to sample, but when we use the method estimate plus or minus margin of error to get an interval based on each sample, C% of these intervals capture the unknown population mean mu. So if we're doing a 95% confidence interval, that means 95% of these intervals capture the unknown population mean. So if we continue along with the BMI example, we can construct many confidence intervals around different sample means that we might obtain from the population. and we get the sampling distribution of the mean x bar is normally distributed. The mean of that distribution is the population mean. And we get a whole bunch of confidence intervals, or intervals I should say, around different sample means. Notice there's one here where the interval misses the true values, but all of the others actually contain the population mean. So we don't know what the population mean is, but we do know that 95% of the time we construct these confidence intervals, they will contain the population mean. So, to interpret a confidence level, we say we are 95% confident that all possible samples of a given size from this population will result in an interval that captures the unknown parameter. So, for example, for a 95% confidence interval, to obtain the margin of error, we multiplied the standard deviation by 2. 95% of the data for a normal distribution actually falls within a plus or minus 1.96 standard deviations. We use 2 as an estimate. For different levels of confidence, say 90 or 99%, we would need to multiply the standard deviation by a different value. So here's a formula. For a sample size n from a population having unknown mean mu and known standard deviation sigma, a C confidence interval for mu is given by x bar plus or minus z star times sigma over the square root of n. And the critical value z star, as it's called, is found from the standard normal distribution. Z star is called the critical value. The value for z star depends on the confidence level. So, let me do an example. Average body temperature for humans is 98.6, right? Well, let's test this assumption. So, a random sample of 130 individuals found an average body temperature of 98.25. And we'll assume that the population standard deviation is 0.73 degrees. Construct a 95% confidence interval for the population mean. So the formula for the confidence interval is here. This quantity, this part of the formula is the margin of error. And x bar is our estimate. So for a 95% confidence interval, the critical value, z star, is 1.96. So the margin of error is 1.96 times the population standard deviation, 0.73, divided by the square root of the sample size, and this all cranks out to equal 0.125. That's our margin of error. So to construct the confidence interval, we calculate the sample mean, 98.25, minus our margin of error, 0.125, equals 98.125, and the sample mean, 98.25, plus the margin of error, 0.125, equals 98.375. So, the 95% confidence interval for the average temperature of humans is 98.125 to 98.375. Notice 98.6 is not in there, is it? So we are 95% sure of this result. So we conclude that 98.6 is not the average body temperature as we thought. This sample gives us a significant amount of evidence that the true average body temperature is somewhere between 98.125 and 98.375, not 98.6. Oops. Now, to find the critical values for confidence intervals, we'll use table C. This is called the t-distribution value table. So notice along the top, we have the confidence levels, and they go from 50% up to 99.9%. So we locate the confidence level we're interested in, And then near the bottom of the table, in the row labeled Z star, we locate down near the bottom of the table. Those are the critical values of Z that we'll use for calculation purposes. So for a 90% confidence interval, the critical Z value is 1.645. For a 95% confidence interval, as we saw, it's 1.96. For a 99% confidence interval, the critical value is 2.576. And there are others, but these are the most commonly used. So here are the IQ test scores for a random sample of 31 7th grade girls in a Midwest school district. And we want to construct a 99% confidence interval for all 7th grade girls in the district. So suppose we know that the distribution of all IQ scores for this population is approximately normal with a standard deviation of 15. The mean of this sample here is 105.84. The critical value for a 99% confidence interval is 2.576. So we can calculate the margin of error, the Z value, 2.576, times the standard deviation divided by the square root of the sample size, 15 divided by root 31. And we get a value of 6.94. That's our margin of error. And then the confidence interval is our sample mean minus that value and the sample mean plus that value. So we add and subtract 6.94 to the sample mean 105.84. So we are 99% confident that the mean IQ test score for all 7th grade girls in the Midwest school district is between 98.9 and 112.78. Notice, I'm 100% confident of what the mean for this particular group of 31 7th grade girls is. There's no question about that. So what this process actually does is this allows us to estimate what the mean of the entire population is. Now, to look a little bit at how confidence intervals behave. The confidence interval for the mean of a normal population illustrates several important properties that are shared by all confidence intervals in common use. So we choose the confidence level, and the margin of error follows. We would like a high confidence and a small margin of error. So high confidence suggests that our method almost always gives correct answers. A small margin of error suggests that we have pinned down the parameter precisely. So let's look at the margin of error to begin with, that part of the formula. So we have Z star times sigma over the square root of n. The margin of error gets smaller when Z star gets smaller. That is, if we choose a lower level of confidence. So the width of the interval is smaller, but we're not as sure about it. We're not as confident. This confidence interval, the margin of error, also gets smaller when the standard deviation is smaller. But we don't have any control over this. The population value is whatever it is. But as n gets larger, 1 over the square root of n gets smaller. So we can choose a bigger sample size to make the margin of error smaller. So to review, we just defined what statistical inference is. We described the reasoning of statistical estimation. We talked about the parts of a confidence interval. We interpret a confidence level, construct and interpret a confidence interval for the mean of a normal population, and describe how confidence intervals behave.